So we've just seen these two plane drawings of K4, and we also saw a plane drawing of K2S. So we know that K4 and K2S are planar. Let's look at the one step more complicated graphs, namely the complete graph K5 and the complete bipartite graph on 3 plus 3 vertices. So as you see here, there are lots of crossings, but maybe just as in the case with K4, we can draw edges in a smarter way so that in fact the graph is planar, and we've just drawn it here in an unnecessarily complicated way that causes crossings. Is that the case? Well, in fact, no. As we will prove in a minute, the graphs K5 and K33 are non-planar. No matter how you draw them, no matter if you take this edge outside or whatever you do, you will have some crossing somewhere. So how do you prove such a thing? Well, for that you need a deep fact from geometry that seems kind of obvious, but that we still need, and that is that if you draw a continuous closed curve in the plane, so continuous, you just keep the pen on the plane, and you draw some kind of curve, and you go back. This theorem has nothing to do with graph theory. It's just about drawing a curve in the plane. So this dinosaur-shaped curve, it can be shaped any way it does, but as long as it doesn't intersect itself, it will separate the plane in two parts. The inside, which has somehow a bounded range, and the outside. This theorem might look ridiculously obvious. Any 5-year-old child would be able to tell you this, but it turns out that obvious as it is very complicated to prove. This theorem is due to the mathematician Camille Jordan, who lived in around the last turn of the century, and it's called the Jordan curve theorem. And for those of you who work with geometry on computers where you have pixels, that theorem in that setting might not be true. But we're not in that setting now. We now have actual plane curves, and so each plane curve divides the plane into a bounded inside and an unbounded outside. So, armed with this fact from geometry, let's prove that K5 and then also K33 are non-planar. We'll take them one at a time. So let's start with K5. So let me put the argument up, and then we'll go through it step by step. So we're supposed to prove that there is no way to draw K5 so that I avoid crossings. So assume it's possible, and let's see that we get a contradiction. So if K5 has a plane drawing, then, well, what does K5 have? K5 has this cycle, U, V, X, Y, Z, U, the outer cycle. And this cycle is a closed curve, and so it has to be drawn as a cycle, otherwise I would intersect myself at some point. So let me go through this again. So in any plane drawing, I must have this cycle as a cycle. U, V, X, Y, Z. And again, why is that? Well, that's because I have this cycle in the graph, so it has to go somewhere. And the only way to draw it in such a way that I don't get intersections between the edges is that I draw it just as this pentagon. So now, once I have the cycle, I have the inside and I have the outside. So let's look at the other edges. The goal is to fit all the other edges in a nice way. So let's look at the edges XU and VY. So this is XU and this is VY. And the question is, can I draw them on the inside, or can I draw one of them or both of them on the outside? Remember, like I did with the diagonal edge of K4. Well, if they are both on the inside, since they sort of go between vertices that are across from each other, they will intersect each other. And if I draw both of them on the outside, so Vy and XU, then however I do, they will intersect on the outside. So I can't do that. So what has to happen is that one of them has to be drawn on the inside and one of them has to be drawn on the outside. Without laws of generality, let's assume that XU is drawn on the inside and then Vy must be drawn on the outside. If it's the other way around, you can use the exact same argument, but one of them on the inside, one of them on the outside. So let's make this choice. Okay, so these vertices are now good. These edges are now good. So let's look at some other edges. So this edge XZ, if I draw it on the outside, I will intersect the blue edge Vy. So it can't happen. And even if I draw it, okay, maybe this is bad, maybe I should draw it here, but then I will also intersect somewhere. So I can't do that. It has to be drawn on the inside. And by the same reasoning, the edge the edge VZ, if I draw it inside, it will intersect this blue line, so I have to draw it on the outside. So far, so good. But now, what edge am I missing? I am missing the edge that goes from U to Y. So if I draw this edge anywhere on the inside, since it's inside this quadrilateral, it will have to cross the red edge XZ. So I can't do that. But if I draw it on the outside, then it will have to intersect this red edge. Well, that's not good either. And the same if I draw it on the outside in any fashion, like I can go all the way like that, I will still have an intersection. So that cannot happen. In other words, there is no way to draw the edge YU so that the graph doesn't have intersections. Therefore, there is no way that this plane drawing is going to work, and K5 is not planar. So in words, the last edge UY would intersect XZ if drawn inside and VZ if drawn outside. So I get a contradiction. The graph is not planar. So that was the story with K5. It is not possible to make a plane drawing of K5. It's not just that we failed at the first attempt because we were not good enough. It's just not possible, as we have proved. And now we'll prove the same thing for K33. And the argument is similar. So again, let's assume it has a plane drawing and see that we get a contradiction. So now we have a cycle in this graph, the cycle that goes A to E to C to F to B to D to A. So this cycle, since it is a cycle, must be drawn as a cycle, otherwise I will get intersections. This is the same reasoning as for K5. So I have A, E, C, F, B, D, A somewhere in my graph. So now what edges do I have left that I need to fit here? I have the edges AF, BE, and CD. So each of them has to be either inside this cycle or outside, because the cycle divides my plane into inside and outside. So the point of Jordan's theorem is precisely that if the edge starts on the inside and goes out, then it will have to cross my hexagon. So let's start with BE and CD. And life is hard enough as it is. Let's forget about AF for the moment. So BE would go here if I draw it inside, and CD would go here. So I can't draw both inside. And you can check that if you draw both outside, then they will also cross in the same way that they did the edges of K5. So let's draw one of them inside and one of them outside. So maybe let's have BE on the inside and then CD on the outside. And now you can see that any attempt to draw EB on the outside would intersect my CD. If you choose to draw CD on the inside and BE on the outside, that will work as well to lead to the same result. And the result is that now I still have my edge AF that I need to draw somewhere. So if I draw AF on the inside, well, it has to cross, it starts in this bounded region and it ends in a different bounded region. So by the Jordan theorem, it has to cross the boundary somewhere. And likewise, if I draw it on the outside. So that is not good. And this sad conclusion leads us to conclude that K33 is not planar. So what I just said was that the edges BE and CD cannot both be inside or outside because they would intersect. But then if one of them is inside and one of them is outside, AF will intersect one or the other. So therefore, K33 is not planar. Okay, so it might look like we went through a whole lot of trouble only for two graphs. If we're going to continue this way, we'll never get anywhere. There are infinitely many graphs that we have to decide if they are planar or not. But actually, it's not that bad. So let's think about some consequences of what we have just said. So if you have a planar graph, then every subgraph of that graph is planar. Pause and think why this is the case. Well, this is the case because if you manage to draw the big graph on a plane, then simply just delete the edges and vertices that are not there in your subgraph, you will get a plane drawing of the subgraph. So if you can draw, say, this graph in a plane, then surely this part of it can be drawn in a plane. So this means that if a graph is planar, it cannot contain any subgraph that looks like K5 or K33 anywhere, because those are not planar, and every subgraph would have to be planar. So any graph containing a subgraph isomorphic to K5 or K33 is non-planar. As a corollary, the complete graphs on n vertices are non-planar for all n greater than or equal to 4. So we've seen that K4 is planar. For the smaller ones, you can draw and check. But since Kn has a subgraph of isomorphic to K5, if n is greater than or equal to 5, then the larger Kn's will not be planar. Similar reasoning for the complete bipartite graphs, because if KRS is such that R is greater than or equal to 3 and S is greater than or equal to 3, then it has a subgraph that is isomorphic to K3, 3. This is an exercise for you to check that KRS, when R and S are both greater than or equal to 3, has a subgraph K3, 3. Since that is not planar, then those bigger KRS are not planar. So either R or S has to be smaller than or equal to 2. And for all these cases, we have already seen, or it's easy to see, that they are planar. But there is something very remarkable. All this is kind of straightforward. So now you might think that, okay, complete graphs and complete bipartite graphs, fine. But surely there are infinitely many graphs, and there might be many, many, many reasons why a graph is not planar. But in fact, no. It turns out that any graph you take is non-planar if and only if it contains a subgraph that is similar in some way that we will have to define precisely to K5 or K33. So basically you look into a graph. If you can see K5 or K33 or something similar to them sitting inside, then the graph is non-planar. If not, the graph is planar. This is extremely remarkable and extremely odd, because this means that among all the infinitely many graphs, only two essentially can ruin planarity, K5 and K33. They are the bad guys in the graph world.